Okay, welcome to another session of Simplified Med Academy teaching series, where we'll break down difficult topics into the most simplest way you can ever imagine. This beautiful day, we'll be looking at tubular processing. I'm always shocked when students find it hard to understand tubular processing after reading it over and over again. I was once in your shoes also. I even didn't like renal physiology at first, but it's time. It made sense. And I want to teach you how it made sense. Let's simplify it. Now, before I first start, let me tell you something interesting. Do you know that I hope this is not new to us? This is a capillary, this is the glomeruli, this is the peritubular capillary, this is the nephron. I hope it is not new to us that about 180 liters of blood is filtered per day by this system. But the amount, or do you think you urinate 180 liters? I'm sure nobody here urinates up to 180 liters. Your maximum urine should be about what? 1.5 to at least 2 liters. So what is happening? How did 180 liters become 1.25 liters? That is just the mechanism of tubular processing. Are you following me? It's basically how this 180 liters that was filtered through your daily GFR became your total output urine of 1.5 to 2 liters. Now, when we are talking about tubular processing has two components of it. It has one part which we call secretion, and it has another component which is called what? Reabsorption. And so under the course of this video, we'll be looking at two aspects: secretion and what? And reabsorption. Are we following? Now, how is urine formed? I'm just setting a basic foundation for now. How is urine formed? If you agree with me that this is how urine is formed, first of all, GFR, glomerular filtration. How this blood in this glomeruli is going to be filtered, right? That's step one. Information of urine. Step two, information of urine is what? Tubular processing, TP. While step three is what? Countercurrent mechanism and ADH action. You can just call it, maybe you can call it the mechanism of urine concentration and dilution. Let's put it as UC and UD. This is how urine is formed. And last week, we have looked at what? GFR. So this week, we'll be looking at what? Tubular processing. Is it clear? And I said tubular processing has two components to it: secretion and reabsorption. Now lay the foundation. What is secretion? What is what? Reabsorption. Tubular processing, it means what? The processing of, now this is the capillary. This is where blood is flowing through. Blood is flowing through this place. I need to be filtered through this place inside the what? Inside the urinary tubule of the nephron. Now, the process at which all this thing that is inside this nephron, if it is flowing like this, the process at which they are going to do what? Modify to form urine. We can still say that is what? Tubular processing of tubular fluid. And when we are processing tubular fluid, we are looking at two things: secretion and what? Reabsorption. Are you following me? Now, what is secretion? Secretion basically is what? Movement of substances from the peritubular capillary. That is the peritubular capillary here, right? Secretion is basically what? Movement of substances from the peritubular capillary into the what? Proximal convoluted tubule. When substances move from this place to this place, that is what? Secretion. When substance move from this place to this place, when substance move from this place to this place, that means when substance move from the tubule of the nephron to the peritubular capillary, that is what? Reabsorption. Reabsorption is when you are moving from here to here. Secretion is when you are moving from the peritubular capillaries to what? Lumen of the nephron. Is that clear? Now, after you have looked at what? As that basic thing, okay, let me add one more thing here. I hope you agree that this is the proximal convoluted tubule. And if you remember, if you watched my first video, I already told you that prox tubule has two parts: the compactor part and the rector part. Now, what next that I want to now show you in this introduction is that you see, as we have said that it's coming like this and it's going like this, you see in this point of this proximal convoluted tubule, substances move. There are two ways in which substance can move from this place to this place. That means reabsorption. Reabsorption can go through two mechanisms. That means substances can move from the tubular fluid to the peritubular capillaries in two ways. Number one, either through what? Paracellularly, or what? Transcellularly. What am I trying to tell you? What I'm telling you is very simple. Is that you see, movement of substance from this place to this place, it can either pass through this cell. Look at this thing I drew in blue. That's the proximal convoluted tubule cell. The cell of the what? PCT. That's what I drew in blue. So if I'm moving substance, let me say that maybe, let me draw a beautiful man. Let me draw him here. Let me draw him in this place. My markers are not writing that much. Let me draw a beautiful man. He's happy to be here. So the process in which this man here, if he moves to this peritubular capillary and it is passing through this PCT cell, that is what? Transcellular. It's moving through the cell. That's transcellular. But if this man, if he move like this, maybe this in here, is happy again, and he move like this, you can see. Are you following me? He move like this. It's look at it is moving. This is the PCT cell in blue. PCT cell in blue. It is moving in between the PCT cells. So we call it what? Para. When you hear the word para means beside. Paracellularly, meaning what? It can either, the process in which reabsorption occurs, it can either be what? Transcellularly or what? Or paracellularly. Either it move through the cell of the PCT or it move beside the cell of the PCT. Now, one more thing I want to let you know is that between two PCT cells, there is something here. Between each PCT cells, there is something here. We call it what? Tight junction. Let me draw this thing. Let me draw it in this place here. Okay, let's do it like this. I just want to draw the PCT back at this point to show you what I'm trying to say. This is one PCT cell. This is another PCT cell. Right? Now, in between these two PCT cells, there is always going to be what? There is something connecting these two PCT cells together, and it's called what? Tight junction. Tight junction. That is what is connecting the two PCT cells. This is the PCT cell A, PCT cell B. What is connecting both of them is what is a tight junction. Now, remember, what I want to let you know is that when they say it is a tight junction, it does not mean that it is not allowing substance to pass through, because now when our concept of tight junction means it is tight, nothing can pass through. Yes, but you see, in the PCT, the tight junction in the PCT, it allows for substance to pass through. So if they ask in MCQs, be very conscious of that what? The tight junction in PCT cells allows substance to pass through. What is this tight junction doing? The tight junction is only helping to hold the PCT cells together. It's very important. And the tight junction in nephron of the PCT is just holding the PCT cells. PCT means proximal convoluted tubule. It's just to hold the PCT cells together. Are you following me? So that is that about that. Now, one more thing I want to let us know again is that you see, we have said that what this reabsorption can be what? Transcellular or paracellularly. Now let's look at the mechanism of transport. The mechanism of transport. I want you to listen attentively to this part, because that is what we are going to build up on when you are moving forward. Mechanism of transport. What is the mechanism? Number one is what? They can either move through a simple diffusion. That means when substances are moving from here to here or from here to here, they can either move through what? Simple diffusion. They can move through simple diffusion. They can move through what? Facilitated diffusion. Facilitated diffusion. They can move through what? Primary active transport, PAT. Primary active transport. They can also move through what? Secondary active transport. They can also move through what? Pinocytosis. That means when cells are moving through maybe secretion or reabsorption, they can follow any of these what? 5 ways. Now, if it is simple diffusion, what does simple diffusion mean? Just basically what? Diffusing from one point to another without the use of any protein or any energy. What is facilitated diffusion? Movement from one point to another. Still same diffusion, but here you are going to be using what? You're using a protein in facilitated diffusion. You are using a protein, but you are not using what? ATP. Now, these are my concerns. PAT and SAT. I want us to understand what we mean by PAT and SAT. PAT, primary active transport. What does primary active transport mean? Let me get some parts that I can be able to write on. I want to explain PAT so we can understand it and be able to apply it, because we need it a lot when we start explaining some things, right? So I'll first draw a cell. So I used to explain primary active transport. Let's say we have a cell like this, right? We have a cell like this, right? Now on this cell, we now have something like, let's say we have a transporter like this. This is a transporter. Maybe hydrogen is binding here, potassium is binding here. Are you following me? So now let's now say on this place we have this thing I now draw in this place is called sodium potassium ATPase pump. I'm sure you are familiar with this word, right? Sodium potassium ATPase pump. Now, okay, let me use this place to be okay, let's use it like that. Sodium potassium ATPase pump. Let me show you an example of something. Now, this sodium potassium ATPase pump, what is it going to be doing? It is pumping what? Sodium out, Abi? It is pumping sodium out. Just follow me. It is pumping sodium outside of this cell. As it is pumping sodium to leave this cell, look, what I'm trying to show you is that in primary active transport, you are transporting substance based on the energy directly. You see, if I am a substance like this and I am moving forward by the virtue of the energy in me, I'm what? Primary active transport. But if I'm a substance that I'm not the one using the energy directly, I'm getting the energy from somebody, that is secondary active transport. Let's continue what I'm trying to show you. Now, okay, let's just use this to be sodium potassium. This is sodium, this is potassium. Let's just use normal RMP values to explain what I'm trying to say. So now this is sodium potassium ATPase pump. Sodium potassium ATPase pump. It has used ATP. It has pumped sodium out. As it has pumped sodium out, what is going to be coming in? Potassium will be coming in. The basis at which this potassium is coming in is because of this sodium potassium ATPase pump. Sodium potassium ATPase pump is the one that is generating an energy. This is just a rough diagram. Sodium potassium ATPase pump is the one that is generating energy for this potassium to come inside. Are you following me? That this one is the energy source. When this energy source is activated, potassium can enter the cell. Now, as potassium is entering the cell like this, sodium is now following it. Now, if this jangular move like this, now potassium will come inside, sodium will also come inside. I'm just doing a rough sketch. Now, potassium is entering directly because of this pump. So potassium is using what? Primary active transport. But this sodium is coming inside because of potassium has entered. So sodium is what? Secondary active transport. So potassium ATPase, this potassium is entering because of this what? Because the virtue of this pump. If you stop this pump from working, maybe you use something like obeying to stop this pump from working, this potassium will not enter again. If this potassium does not enter again, this sodium does not enter again. It is just to show us that what? This sodium is dependent on potassium, while this potassium is dependent on this pump. So this pump is where the energy is generated from. When energy is generated from this pump, it allows this one to move in. So that is what? As potassium is moving in, it is moving towards primary active transport. Because potassium is moving in, it will be dragging along sodium. I'm just giving a rough sketch here. It is going to be dragging along sodium. So it is dragging along sodium. Sodium is what? A secondary active transport, because it is not sodium that have the energy. It is potassium that has the what? Energy. So now if something is moving with primary active transport, just for simplicity purpose, if it's moving with primary active transport, we do say it is what? It is moving along the concentration gradient. Along what? Conc gradient. If it is moving with primary active transport. Just for in basic concept. Why this is the secondary active transport? We say it is what? Against conc gradient. Are you following me? This is just for basis, just for something basic. And now we basically know what PAT and SAT means. This, like I said, this is not RMP. I'm just using an example to just explain what PAT and SAT means. What about pinocytosis? Pinocytosis is just like the process whereby substances is absorbed into the cell, majorly fluid. Now we call it cell drinking. We have not forget the process by which fluid is entering into the cell. Yeah, that's what we call pinocytosis. And they form a pinocytic vesicle. So now let's now move on. After we have learned about PAT and SAT, one more thing I want to bring to your concept or to your understanding is one beautiful, important thing. What is the component of blood? I'm sure everybody here should know. Blood is containing what? It's containing plasma, right? Plasma and what? Blood cells, right? Blood cells. Now, this plasma contains a lot of things. It contains water, it contains ions, it contains proteins, it contains what? Enzymes, right? Why am I going like this? I want to just know, in a normal condition, I hope you know that protein cannot what? Leave the glomeruli. Blood cells too cannot be filtered at this point. Blood cells, proteins cannot be filtered at this point. What is going to be entering here is basically what? Water and ions. What is entering this place? Because enzymes are protein too, so enzyme cannot be able to what? Diffuse through this place. I'm just trying to relate something to you that all the whole thing will be looking at that. What is going to be processed in this tube is basically what enters the tube. What we are processing in this tube of this nephron is what enters the tube. Now, and I've explained to you that blood cells are too big. They cannot move from this place to this place, so they cannot be what? Processed. Enzymes and proteins, they cannot be what? Moved from this point to this point because they are what? They are too big. But water and ions, they can what? They can be filtered from this point to this point. I follow me. They can move from the glomeruli to the what? To the PCT. Is it clear? Right. Now, we will now look at how does this ion work? How are they processed? Now, this ion, we can have sodium, potassium, magnesium, calcium, the likes, phosphate, and every single thing. We will now look at how these ions are processed in this tube. How these ions are processed in this tube. And before we go to that part, let me just label this nephron again for educational purpose. Is that you see that this is the word glomerular capillaries. This space is the Bowman space, or you can call it the Bowman's capsule. While this area is the urinary space. This point here, from here to here, is the what? Proximal convoluted tubule. And don't forget that PCT can be divided into two parts. An initial part, which is called what? Pars compacta, and the lower part, or the last part, which can be called pars recta. Pars compacta means it is very convoluted. You can call it pars convoluta. You can call it pars compacta. It means it is very convoluted and all of this type of thing. Why the pars recta is straight. Recta. When you hear the word recta, it means straight. So the first part of the PCT is what? Highly convoluted. While the second part is what? Straight. So this part is the loop of Henle. This is the descending loop of Henle. You can see it's coming down. Descending loop of Henle, ascending loop of Henle, thick ascending loop of Henle. Loop of Henle, LOH. Can see this one is thin. Thin descending loop of Henle, thin ascending loop of Henle, thick ascending loop of Henle. After this thick ascending loop of Henle, we now have what? Distal convoluted tubule. This is the distal convoluted tubule. The distal convoluted tubule can also be grouped into two parts. The DCT, you can put into what? Early DCT and late DCT. This is the early DCT, this is the late DCT. Right? After that, then this is the what? Collecting duct. Is that clear? So we'll now look at how ions are processed at every single segment of the nephron. How is ion processed in every single part of the nephron? Now, what I will now do is that I will pick PCT, I will list the ions, and I will list how they are processed. I'll pick loop of Henle, I will list the ions, and I will explain how they are processed. I'll pick the DCT, I will list the ions, and I will explain how they are processed. I'll pick the collecting duct, I will explain how they process their ions. Is that clear? We will pick this PCT now. Let's draw this proximal convoluted tubule. I will draw this part, this initial part of the PCT. I will draw it here in a very big version. After I've drawn it, I will explain. Then I'll come to this late part of the PCT. I will also draw it in an enlarged format and we'll look at what is happening. Right. So let's look at this PCT, this initial PCT. Let's look at it in a much bigger version. So this is the edge. It's coming like this. This is the PCT beside it. This is the PCT cell, right? So let's just put it for formality purpose. It's looking like this. So just for formality, okay, let me make it look much more better. I just pick one part of the PCT. So let me explain what is happening. So substances have been filtered. Water and ions, like I said. So basically what we are dealing with is what? Water and ions. They have been filtered. Now let's now pick one of the first one. Let's pick sodium. I'll pick sodium. I'll explain for sodium, water, glucose, hydrogen ions, HCO3, and I'll explain for potassium. Yeah, maybe chloride. Let's just say chloride. So I'll explain how all of these things are processed in the PCT. So let's imagine all of them like this. They are inside this tubu, they have entered this tubu. They are in the initial part of this PCT. Now, first of all, this part here, now this is a lumen. This is a lumen. This is a lumen of the tube. So this black thing here, it is called the lumen of the what? Lumen of the it is called, you can always call it luminal membrane. Luminal membrane, because it's at the lumen side, luminal membrane. Why this part is the what? Basolateral membrane. Let's call it BL. Basolateral membrane. This is the basolateral, this is the luminal membrane. Now on this basolateral membrane, there are going to be a pump known as what? Sodium potassium ATPase pump. On this part here, we'll have them around. Sodium potassium ATPase pump. This red are what? Sodium potassium ATPase pump, NK. Sodium potassium ATPase pump. Now, what are these sodium potassium ATPase pump doing? Sodium potassium ATPase pump, they will be what? From the word Nokia, don't forget, Nokia. Sodium potassium ATPase pump, sodium, NO, sodium is out, potassium in. So you don't forget function of sodium potassium ATPase pump. Sodium potassium ATPase pump, what do? They follow the phone Nokia. NO, sodium out, Ki, potassium in. So that is how they are working. They are pumping what? Sodium outside. They are pumping sodium outside. And they are what? Pumping potassium inside the cell. They are pumping potassium inside the cell. Are you following me? They are pumping sodium outside. All of them are pumping sodium outside and are pumping what? Potassium into the cell. Now what are they now going to do? And if you remember from basic physiology, you should remember that this pump, they are going to be pumping what? They will be pumping 3 sodium outside, 3 sodium outside and 2 potassium inside. Just not to bore you with too much talk. Everybody here should at least know that what? That this pump, it is causing an electronegative state. That we are pumping 3 positive outside. They are pumping 3 positive outside. They are taking 2 positive inside. This is later going to give you what? Negative. Just as if you are receiving 30 million. Okay, let's say you are receiving 30 million, but you are spending the whole 30 million and you are receiving just 20 million back. With time, you will get broke because what? The positive that is going outside is not equal to the positive coming inside. Positive going outside is more than the positive coming inside. So later on, it's going to make this cell of the PCT to be what? Negative. So the cell of this PCT, it is always a value of what? Minus 70 millivolts. Minus 70 millivolts. And there will be a lot of potassium inside. There will be plenty potassium inside this thing. Plenty potassium inside this place. Plenty potassium. Because what? Potassium is coming inside. Sodium is being pumped outside. And because of this ATPase pump, this cell of the PCT becomes what? Minus 70 millivolts. Are you following me? So let's now pick how is sodium going to be what? Filtered. Now this is Mr. Sodium. He gets here. This is him. He's happy. Okay, should we make him happy? He's sad at first. They want to throw him away out of the body. He's sad. He's sad. So how is he thinking, how will I leave this place? Because if he does not get filtered, it's going to come out as urine. He does not want to leave the body. So what's he going to do? When he comes here, look at sodium is what? Sodium is positively charged. Don't forget, sodium is positively charged. Are you following me? Sodium is positively charged. This cell is what? Negatively charged because it's what? Minus 70. The cell is minus 70. Now let's now look at it. Look at positive, negative. Positive attract negative now. Just basic concept. Look at this is minus 70, this is positive. So because this is negative, this is positive. It will be drawing this sodium to want to enter. There will be a pull. Because this is negative, this is positive. Negative attracts positive. We say that like charges what? Like charges repel, or like charges what? Attract. So this is negative, positive. They'll be dragging themselves in. That's one. Number 2, what is also one thing that will be dragging it in is that you see, there is a lot of potassium inside this place, but there is less sodium. Now the sodium is being pumped out, but there's more potassium inside the cell because there's less potassium, there's less sodium. Look at, because there's less sodium inside the cell. Sodium too we want to what enter the cell. That means sodium reabsorption is favored by two mechanisms. Number one is the what electrical gradient, positive negative. Number two is the what concentration gradient. There's less sodium here, there's plenty sodium here. So based on what osmosis, sodium want to move what, and diffusion, it will want to move from a region of highly concentrated to a region of what low concentrated. I mean now, so the sodium want to move. That means sodium is moving through what through processes. But as sodium wants to move, this sodium is highly charged. Are you enjoying my story? This sodium is what, it is positively charged. There are two things already dragging that sodium come, but sodium cannot come because it has a charge. And something that is charged, it cannot diffuse through what? Through this membrane. Anything that is charged, it cannot diffuse through this membrane. It cannot just pass through the membrane. So there will be something on this luminal membrane. There will be something here. Let's use it with color blue. There will be something on this luminal membrane. We call it what? Sodium handling protein. Sodium what? Handling protein. Sodium handling protein. So is that protein that will what? That will facilitate its absorption. It will facilitate the absorption. Now, that means we have already set everything that is going to happen. Now, as sodium is entering, sodium is a very good man. Why is he a good man? As it's entering, it will drag along somebody together with him. It will drag along somebody together with him. Okay, let's say that this is not okay. Let me make it like this. This is sodium here. It can drag amino acid. Yes. So now, look at this sodium potassium ATPase pump. It is pumping sodium outside. Potassium is coming inside. So it is because this pump, this is what is powering this thing. Hope you remember PAT and SAT. This pump of this sodium potassium ATPase pump, it is the one that is powering this place. So because there's less sodium here, this pump is powering it. So this thing that is like jangilova, it will shift like this. He said this jangilova, it will shift like this. So it will shift like this, and enter. So sodium will enter and amino acid will also what enter because of what jangilova. Now you should now know that sodium is entering because of what PAT. Sodium is entering due to what primary active transport. Don't forget, it's a common MCQ that sodium is entering through what primary active transport because what this is the pump that is powering it. But as sodium is entering, it will be dragging amino acid. Amino acid, hold me, let's go together. So because it is dragging amino acid together with it, amino acid is entering through what SAT, secondary active transport. Sodium is entering to what PAT, amino acid is entering to what SAT, because amino acid is dependent on this sodium. If you block this pump, this sodium potassium ATPase pump, if you block this pump, this thing cannot work again because it is dependent on this ATPase pump. Now don't forget, anything that is moving through PAT is what? It is moving along the concentration gradient. Anything that is moving through SAT is moving through what? Against the concentration gradient. So if they ask you that sodium is moving what? Through PAT and it's moving what? Along. PAT is along. What about SAT? Against. You can even remember the word against. Look at the word against. Against. So when it's not always, but just like for simplicity purpose, that if it is SAT, you are what? Moving against the concentration gradient. If it is PAT, you are moving along the what? Conc gradient. Is it clear? So that's basically that. So that is how sodium is absorbed, and also how what amino acid is what absorbed. So I've explained how sodium is absorbed. Okay. Now let's look at how glucose is absorbed. Okay, let's look at how water is absorbed. You know, anywhere sodium flow goes, water also follow. So our sodium is moving like this. Now it is dragging this protein, sodium handling protein. It is also pulling amino acid together with it. So water will also follow, because anywhere sodium goes, water follow. So water basically just follow sodium as it is going. And sodium is 65%. 65% of sodium is absorbed in this species. 65% of sodium is absorbed. 65% of water is what is absorbed also. Now let's look at how glucose is reabsorbed. Okay, potassium too, it is moving passively, passive reabsorption, and it's about 65% too. Potassium is moving what? Through passive reabsorption. It is moving because there's also potassium in this place, and they don't really ask it because it's not needed in this point. But it also moves through passive, meaning it's never to just be going by itself normally. Now let's go and pick glucose. Let's look at how glucose is reabsorbed at this point. So let's look at how glucose is reabsorbed. It is still the same mechanism that is occurring that will also occur. Everything I've explained is money, still the same thing. Just that this pump, this sodium handling protein, it will have, okay, let me use this one in the third part. It will have 2 points, sodium, and it's having what? Glucose. This is glucose. So that now there is one that is carrying sodium and amino acid. There will be another one again that is carrying sodium and glucose. Is it clear? Now this pump that is carrying sodium and glucose, it is called sodium glucose transporter 2. Sodium glucose transporter 2. That's what is carrying sodium and glucose from this lumen of the tubule inside this place. So they follow the same process. So that sodium potassium ATPase pump, it makes what? It makes the cell minus 70 to be negative, and there's less sodium inside the cell, and the cell is negative. So because of those two factors, sodium will shift like this. This pump will go like this, just like Jangilova now. This pump will move like this. I mean now, this glucose will follow it like this. So as sodium is moving, glucose is also what? Entering. Is it clear? So that means they follow the same mechanism too. Sodium is entering, glucose is also following it. Sodium is entering towards PAT along the conc gradient. Glucose is entering towards SAT against the concentration gradient. Now when the glucose enters, how does the glucose leave? The glucose moves through what? Glucose transporters, GLUT2. It leaves the cell through what? GLUT2. GLUT2. It enters through what? SGLT2. It leaves through what? GLUT2. Sodium. When sodium enters, how does sodium leave? Sodium leave through this what? Pump, because this pump will pump out sodium. Are you following me? It's his continuous process. As the sodium is entering, it's pumping out the sodium. There will be less sodium inside here. It will facilitate what? Reabsorption of this what? Of more sodium into this place. If you block this pump now, sodium cannot be pumped out of the cell. Sodium will be accumulated in this place. If sodium is accumulated in this place, sodium in this tube cannot move into the PCT. Why? Because just like osmosis or diffusion, now you have to move from a region of high concentration to a region of low concentration. If sodium is already high concentration, substances cannot move from here to here. Substances will rather move from this place to this place because of the what? Conc gradient. Is it clear? So that's why this pump has to always work. Now glucose, 100% of glucose is reabsorbed. 100%. That means all the old glucose is reabsorbed. 100% of glucose is reabsorbed. That is why anytime glucose is very useful in the body, you don't need to throw it away at all. Because anything that is reabsorbed, that is entering the blood to be reused. Glucose is very important. You don't need to throw it away. That's why we absorb 100% of the what? Of the glucose. Are you following me? 100% of glucose. That's what we reabsorb. And if you can see people with glucose in their urine, basically it is showing something that what is high blood sugar. And majorly the blood sugar level in the plasma should not exceed 180 milligram per dl in the plasma. Anytime your blood level sugar is exceeding this value, it's going to most likely appear in the urine. Most likely in physiology, you learn about 200 milligram per dl. You know, we have random and fasting blood sugar. That one is under endophysiology class. Now, that's just the concept about that. Now, what next down? So we have looked at how glucose is reabsorbed. Okay, let's look at how others too are reabsorbed. Okay, let's finish this. Let's finish this tube. Abi now, right? So let's draw another PCT cell. Let's draw another PCT cell beside it. Are you following me? So this is the initial part. This is the what? Later part. So what's happening in this later part? Okay, or should I pick it now? Okay, let me go to this later part first. Let me pick the later part first. It will be better that way. Let me pick the later part. What's happening in this later part? You see, the sodium that is moving like this, bam, it enter here. As the sodium is here, it is moving outside through this what? Sodium potassium ATPase pump. Now, if the sodium is moving outside through this place, what will happen to this outside? This part, it will be filled with what? Excess sodium. There will be accumulation of plenty sodium here. You understand now? Because sodium is being pumped out. There will be plenty sodium at this outside. Plenty sodium, lot of solutes, plenty sodium, plenty glucose, plenty amino acid in this place. Are you following me? There will be plenty here, amino acid, glucose. Are you following me? So because this place is highly concentrated with solutes, water, apart from water moving like this, water will diffuse out through this what? Paracellular way. Water will also diffuse through this part. Because of this place is highly concentrated, water will leave through this what? Paracellular mechanism. And as water is moving, it will pull along chloride. You know, chloride is negative now. Chloride is negative. Now this part that is outside, they are all positive. Sodium is positive. Amino acid is most likely positive. Because of the positive nature of this outside, it will pull the what chloride. Water is coming like this because of the what highly concentrated external solute. That's why water is coming outside. Why this chloride is moving? Due to what? Due to the positive charge of sodium. So the process in which water and chloride are moving through this paracellular part into the peritubular capillary is what we call solvent drag. That's what we call solvent drag. So that's basically how chloride is what also reabsorbed. Though in some textbook you also see how chloride is reabsorbed with formate, phosphate, and the likes. But I will not enter those parts. It's not exam necessary. So let's look at how is hydrogen and HO3, how are they reabsorbed? Let me use the same place again. Let me use the same place. Okay, I've explained glucose. Okay, now this is the same thing as inside the cell. Now how is hydrogen and HO3, how are they reabsorbed? Inside the cell, there's high potassium, absolutely, yes. But there's one more thing inside this cell that is happening, is that there is water inside this cell. There's water and there's carbon dioxide. There's water and CO2 inside this PCT. Now, water and CO2 will combine to give us what? H2CO3. Are you following me? They will combine to give us what? H2CO3 by what? Carbonic anhydrase enzyme. Abi now? This H2CO3 to dissociate to give us what? To give us what? Hydrogen ions and what? HCO3 minus. Is it clear? Water plus CO2, H2CO3 dissociates hydrogen plus what? HCO3 minus. Now, what's now going to happen? What's going to happen? This HCO3 here, just look up, please, don't write. Just follow me at this point. This HCO3 that is here, that is formed, the HCO3 will diffuse out. Let me use this place to just explain. The HCO3 will move outside. This HCO3 that is formed through this reaction, it will move outside like this, through HCO3 channels. This hydrogen that is here, what is now going to happen to this hydrogen? Let me use this thing to explain it. How will this hydrogen work? There's another pump again. This sodium and amino acid, sodium and glucose, they are moving through a symport system. Do you know symport means both of them are going the same way? So there'll be another pump again in that same PCT. There'll be another pump again. Look at this pump. It's like this. Okay, let me use a different color for it, so we don't have color ion. Let us even have color ion, so it will be what? Prominent. So this HCO3 that we form is going to this HCO3 has moved out like this. This hydrogen, you can look at the so look at the hydrogen. So if this pump is working, sodium potassium ATPase pump, now it is pumping sodium outside, then sodium will enter inside. Now, if sodium enters inside, look at it, this is Jangilova. Do you understand? This is the what? This is the Jangilova. If this sodium, if this Jangilova shifts, sodium will come inside like this. Where would this hydrogen ion go? It will go like this. It's a Jangilova, you shift it like this. When you shift it, sodium enters, hydrogen leaves. So hydrogen will now what? Hydrogen will enter into this lumen. Are you following me? This is how hydrogen leaves. Hydrogen binds to this what? It binds to this sodium hydrogen antipode. So when it binds to sodium hydrogen antipode, sodium enters like this, hydrogen leaves. Now, when hydrogen leaves to be inside this place, what will happen to hydrogen? Inside this tubule, let me make it more big. Inside this tube, there's an ion inside this tube called HCO3. There's an ion inside this tube called HCO3. Let me just, so that we can have space here. There's an ion inside the tube called what? HCO3. That's the bicarbonate. So now this pump has worked. It has carried sodium inside. But the sodium only. Then hydrogen what? Is coming outside. Now when hydrogen comes outside, this hydrogen here, what will hydrogen do? Hydrogen will react with this what? HCO3. Hydrogen will react with this what? HCO3. Hydrogen plus HCO3 will give us what? H2CO3. This will dissociate to what? Water and CO2. Are you following me? So this CO2 now, this CO2 will now move. CO2 will move. It will diffuse to this place through simple diffusion. CO2 will move through simple diffusion because this thing is lipophilic and CO2 is a gas. It is lipophilic. So CO2 will enter. When CO2 enters now, CO2 will bind to this water again. Let me come again, because students find this part quite hard to understand. How is hydrogen and HO3, how are they reabsorbed? Is that, you see, this pump, I've explained how sodium, glucose, and all of them work. There will not be a last pump, right? A last transporter. That transporter, what is it going to do? It will pump sodium inside, it will move hydrogen outside. Are you clear? So when it pumps sodium inside, it moves hydrogen outside. When this hydrogen moves outside, it binds to a bicarbonate that is already in the blood before. Hydrogen ion binds to the bicarbonate. When it binds to this bicarbonate, it gives us what? H2CO3. H2CO3 will dissociate to what? Water and CO2. This water is it will go its own. Don't let me speak Yoruba. Water will what? It will go its own way inside the tube. But this CO2 will move back into this PCT. When the CO2 move back into this PCT, it will bind to what? Water. That CO2 that is entering, it is reused to bind with water. When CO2 binds with water, it gives us what? Hydrogen and HCO3. This HCO3, it leaves. So that means HCO3 is reabsorbed in two ways. First from this place and also from this place. This HCO3 is moving through this what? HCO3 channel. While this hydrogen that is formed, it's moving into this what? Lumen, by using what? Sodium hydrogen exchanger. Is it clear? So that's basically how we have explained. So now one more thing I want to add to is that hydrogen is what? Secreted. HCO3 is what? Reabsorbed. Hydrogen ion is what? Secreted. Look at, it's going like it is secreted, but HCO3 ion is what? Reabsorbed. In the PCT, hydrogen ion is what? Secreted. So the HCO3 is what? Reabsorbed. So I've explained how this and this are done. Are you following me? One more thing I need to tell you is that what? 85% of HCO3 is reabsorbed. 85% of HCO3 is what? Is reabsorbed. Others apart from this one I've mentioned, they are also 65%. Any ions in this PCT apart from one I've mentioned, they should also be 65% also. Why? Because they are following sodium. So basically, since sodium is 65%, they should also be 65%. So that's basically how PCT works. So from the PCT now, I'll move to the what? Loop of Henle. I will explain how these ions are also reabsorbed in the loop of Henle. Is it clear? So I hope what I draw here, it is not confusing. I've looked at the PCT. So I just pick this loop of Henle part and I draw it in an enlarged version so we can see what is happening. And don't forget that the loop of Henle has three parts. Loop of Henle has three parts. Thin descending loop of Henle, thin ascending loop of Henle, thick ascending loop of Henle. Thin descending, thin ascending, and thick. Thin descending, thin ascending, thick ascending. Now, the three of them follow different ways. They work in what? Different ways. There are three things that they work in different ways. Now, I will only be focusing on the ions that are important in exam and MCQs. Are you following me? So basically, what is happening in this PCT? Okay, let me just draw this so as to just for all sense of what is happening in the PCT? This thin loop of Henle. Okay, let me say that this is, we have filtered some things at this point, Abi. So let us say that we have water here. This is water. This is water, right? And inside this water, we still have some ions because it's not everything that is reabsorbed at the PCT. The PCT is the primary site of reabsorption. It's the major site of what? Reabsorption. It is the most energetic site of the what? Nephron too. In case MCQs require that. Let me draw. I want to draw an ion. Yeah. I want to draw a let's make them sad. They have not been reabsorbed. Some of them have not been reabsorbed. Right, so this point is containing water and what? Water and ions. Now what's going to happen? At this thin descending loop of Henle, what is reabsorbed here? You know that at this PCT, we have thrown a lot of solute outside. There are plenty of solute outside. If you remember, sodium, potassium, bicarb, all of them, they have been thrown out, Abi. They are here like this. This is the blood region. They have been thrown out. So this place, it is highly concentrated because when we look at the last part of urine formation, which is what? Urine concentration and dilution. This part, we'll use it a lot because this is the concept of what? Countercurrent mechanisms. Are you following me? So, but we are not entering that part yet. We are still in secretion and reabsorption. Now, this part is highly concentrated with solute. Now, because it's highly concentrated with solute, water will leave the what? Tube. At this point, at the thin descending loop of Henle, what is leaving? Water. Water is leaving at the what? Thin thin descending loop of Henle. Why? Due to what? The external part is containing a lot of solute. Are you following me? Water is leaving. Now when water leaves, the fluid is going to become what? More concentrated. Are you following me? So what's going to be happening at this thin ascending loop of Henle? This thin ascending loop of Henle, it reabsorb passively few amount of sodium. But passively few amount, like it is not really needed. But in case they also ask you thin ascending loop of Henle, it basically absorbs sodium passively. Why the thin descending, what's it absorbing? Water. The thin ascending, what's it absorbing? Passively. Look at passively. It is not needing sodium potassium ATPase pump, sodium handling proteins, not needing all those things. It's just going out passively, and just very minute amount is actually leaving. Now let's look at the thick ascending loop of Henle. So let's draw the cells of the thick ascending loop of Henle. I'll just draw one cell of the thick ascending loop of Henle. I'll draw one cell to represent the thick ascending loop of Henle. Now this thick ascending loop of Henle, it has one beautiful thing. Please listen. Stop writing also. At this point, it has something. This is the basolateral membrane, this is the luminal membrane. On the basolateral side, it has the sodium potassium ATPase pump. This green, that's the what? Let me just put it as sodium potassium ATPase pump. That's the green. Apart from this green, it now also have one more thing. We call it what? NKCl. It means what? Sodium. This marker is not giving me what I need. Sodium potassium chloride. That means what is on the basolateral part of the thick ascending. There are three transporters: sodium, potassium, chloride co-transporter. They are what? Co-transporter. That means all of them are what? Entering. There's also sodium potassium ATPase pump. Just follow me. On the basolateral side, there's what? Sodium potassium ATPase pump. And also on the basolateral side, there's what? Sodium potassium chloride co-transporter. Or you can call it sodium potassium 2 chloride co-transporter. What am I trying to tell you? Is that, you see, this is a sodium. It allows sodium enters. One sodium. It brings in one sodium. Potassium. One potassium. But how many chloride? It brings in 2 chloride. Let me use something more legible. It brings in 2 what? 2 chloride ions. 2 chloride ions, right? So that means what? 1 sodium, 1 potassium, but 2 chloride ions. That's what it's bringing inside. Just follow me, please. I want you to understand this thing. Now, this sodium that enters, it will leave based on this sodium potassium ATPase pump. This green is the what? Follow me first. This green is the sodium potassium ATPase pump. This sodium that entered, it will leave because of this pump. Now this pump is pumping what? Sodium outside. It's pumping sodium outside. It is pumping potassium inside. Abi now. So this sodium that entered, it will leave through what? Sodium potassium ATPase pump. This chloride that enters, there will be a channel here. There will be a chloride channel down here. This chloride that entered, it will leave through this what? Channel. Just follow me first. Sodium is leaving back through the sodium potassium ATPase pump. Chloride is leaving through this what? Chloride channel. Now this potassium is leaving through 2 ways. It's having one part here. It's having one place here. This one is called potassium leaky channels. It's having a place here for it that it can leave out. Potassium can leave out through this place. But not only that place, it also have some points here where it can mean potassium can leave outside and potassium can also enter into the cell. Just follow me first too. Now this one, they're called RUMC, not RUM, sorry. They're called RUMC channels. Now, let's just follow our story. This potassium that is entering this here, it is through what? RUMC channel. Hold on. RUMC channels. Now, they will be bringing, okay, let me tell you the sweet part. Is that this pump, this sodium potassium 2 chloride co-transporter, we call it an electrogenic pump. Just follow me first though. You will see what is happening. Electrogenic pump. Why is it called electrogenic pump? It is called an electrogenic pump because it causes a charge inside this tubule. You know, this is potassium ions. Potassium ion is entering, it is carrying a positive nature, abi. Now when this potassium enters this place, it will bring a charge of plus 10 millivolts inside. Why am I highlighting this point? You will see it now. Let me come again. On this place, there's a basolateral membrane and a luminal membrane. On the BL membrane, we have sodium potassium ATPase pump, sodium going outside, potassium entering. We also have 3 more pump. So NKCl co-transporter, taking one sodium in. Sodium that enters will leave through this pump outside. Sodium goes outside, potassium enters. This potassium that enters, it leaves through 2 ways. First of all, one leaves through the potassium leaking channels, one enters the cell through the what? Rhomb channels. While this 2 chloride that enters, it leaves through what? Through chloride channels, basically. So this potassium that enters this pump, this tube, it brings about an electric nature, because this potassium is bringing about an electric nature into this lumen. That's why we call it what? An electrogenic pump, because it's bringing a positive nature into this lumen. Now, this positive 10 millivolts, what's it going to do? This positive 10 millivolts will help us to reabsorb substances like calcium and magnesium. Calcium and magnesium. Are you following me? This pump is what is helping us. So that means, okay, let me put it here that part of the DCT, part of the thick ascending loop of Henle. Let me use here. That's okay. Just to show that it is in part of the thick ascending loop of Henle. Calcium and magnesium, they will leave through the bases. Don't forget that calcium and magnesium are moving through the basis of this what? Of this positive nature of this lumen, which is brought about by the what? By the potassium. If you block this co-transporters, so NKCl, you cannot absorb calcium and magnesium. Are you following me? So that's how calcium and magnesium are what? Are reabsorbed. So apart from that, one more thing I want us to know is that you can see this part. Look at this part is what? Absorbing water only. This part, passive sodium. This part, it is absorbing only solute. Look at it, is worth repeating that the thick ascending loop of Henle is only absorbing solute. It does not absorb water. It does not reabsorb water. It only reabsorbs solute. Because it reabsorbs solute, sometimes we call it the cortical part, like the cortical diluting part. Like it's absorbing only solute. Solute is leaving, so we can call it what? The diluting part of the nephron. Some people call it the diluting part, because as solutes are leaving, the fluid inside is now becoming what? More dilute. Some people call it the diluting part of the nephron. So that means solute leaves. Now, we have looked at how calcium and magnesium leave the cell. Now, how does sodium leaves? Sodium basically leave through that same process we are talking about. Sodium, look at this, is this pump. It has pumped sodium outside, it has pumped potassium inside. Inside this place is what? Is deficient of sodium. Because there's sodium deficient in this place. Sodium will move from this what? Lumen to enter this place. This is sodium. And about 25% of sodium, 25% of sodium is reabsorbed through this place. Sodium will be reabsorbed, right? Sodium enters and it leaves through this place. Little bit of potassium is also reabsorbed. Basically, you can say 20% of potassium is also reabsorbed at this point. Potassium is also reabsorbed. And some little amount of chloride. But the major thing I want you to know here is what? About this electrogenic pump, the Rhomb channels, how calcium and magnesium are reabsorbed. And also, don't forget that this place, it can be, okay, I'll still look at diuretics, but let me just tell that this loop of Henle can be blocked by loop diuretics, but we'll still look at diuretics. So basically, that is how this thick ascending loop of Henle, that is how it works. Is it clear? Now, one more thing I want to add is that, look at, let's complete this thing. At the early part of the DCT, this is the thick ascending loop of Henle. This is the word DCT. This is the early DCT. Early DCT works just like this thick ascending loop of Henle. Early DCT, it works just like this ascending loop of Henle. Now, how does early DCT act? On its own, it has what we call sodium chloride channels, or basically sodium chloride transporters, or sodium chloride co-transporters. Are you following me? What DCT acts, or how it does its own, is that it uses its own like this. It's going to be reabsorbing sodium and chloride. Are you following me? It's also having sodium potassium ATPase at this point. Sodium potassium ATPase. So they are pumping sodium outside and are bringing potassium inside. Now this sodium chloride will also leave because of this what? Inside this place is less of sodium. So sodium leaves. When sodium enters this place, Sodium will leave through the sodium potassium ATPase pump. When chloride enters, chloride leaves through what? Chloride channels. Are you following me? That sodium leaves through the sodium potassium ATPase pump. Chloride leaves through what? Chloride channels. Don't forget, because they usually ask, they can ask that what is the mechanism in which sodium is reabsorbed in the thick arsenic loop of N? It is through what? Sodium potassium 2 chloride co-transporters. But if they ask you how is sodium reabsorbed in the early DCT, it is through what? Sodium chloride co-transporters. It is what repeating. Sodium chloride and sodium 2 chloride are two different mechanisms. Exactly. So basically, that is how this loop of N work. Now we'll now look at the last part, which is what? The collecting duct and the late DCT. How does the collecting duct and late DCT, how did they work on their own to also what? Reabsorb substances. So now let's look at how the collecting duct and the late distal convoluted tubule act. Basically, they work through the same way. But let me explain it in a much better way. You see these cells I draw in blue, we call them intercalated cells. Those ones in blue are called intercalated. While those ones in red are called what? Principal cells. That means on this part, this last part, there are two types of cells: intercalated cells and principal cells. So intercalated, from what? Intercalated. This calated, it means cell. So intercalated means between cell. Meaning if I have somebody here, are you following me? And I have somebody here. This one in red is intercalated. It is between two things. It is intercalated. Is that clear? Intercalated basically means between cells. Now, these principal cells, why are they called principal? You know, when you hear the word principal, what's it telling you? It's telling you dominant. No, from your secondary school, what's the highest level? It's principal. Just like in the university, the vice chancellor. So, anyone you want to use. But what we are trying to tell you that principal cells means dominant. So the principal cells, why are they called principal cells? They are called principal cells because they are the dominant type of cell. In this part, collecting duct and the late distal convoluted tubule, the most dominant cell are the what? Principal cells, which I drew in red. Why this blue? They are the what? Intercalated cells. They are less in number. Principal cells are much in number. So we'll look at how the intercalated cell work. After we look at that, we'll look at how the principal cell works. Then one more thing I want to add is that this part, which is the late distal convoluted tubule and the collecting duct, they are called fine tuners. They are called what? Fine tuners. Why are they called fine tuners? You know, when you have done everything perfectly, you have done it very beautiful, you're not trying to add some extras, maybe extra sweetness. Are you following? Like extra sweetness to make it more sweet. You have served the purpose. Okay, let's assume you go for a haircut in a barber shop. The barber has done, he has cut your hair, it is all good and nice. But the barber might still take some time to carve and make it look more nice. It's fine-tuning the process. You have done every single thing that needs to be done, but just trying to make it more neat. So the fine-tuner part of the nephron is just the late distal convoluted tubule and the collecting duct. So let's look at how the intercalated cell works. Okay, let me make this intercalated cell. Let me make it more big. Yeah, let me make it in a much more bigger way. Let me enlarge it down. Okay, one thing I wanted to add is that electroneural pump. I wrote something, electroneural pump. That sodium chloride co-transporter, LEDCT. Now, LEDCT has sodium chloride co-transporter. Sodium chloride co-transporters are called electroneural pump because they do not cause a charge in this lumen. But sodium potassium 2 chloride co-transporters are called electrogenic pump because they cause a charge inside the lumen. Need to add that. So let me make this cell much more bigger. I drew it out of proportion, obviously. But let's look at what is happening. Inside this place, look at. Inside this place, what's happening? There is going to be, why this marker is bad? There will be water plus CO2. Intercalated cell. Don't forget that we have intercalated type cell A and intercalated type cell B. We have two types of intercalated cell. Type cell A and type cell B. I will not enter type cell B. I'll just talk about type cell A. Right? But when you're looking at metabolic acidosis and alkalosis, how the renal compensations, you look at type A and type B, but just look at basic level here. So water plus CO2 react, it will give us what? H2CO3, right? This is going to give us what? Hydrogen plus HCO3 minus. Is it clear? Thank you. Now, this hydrogen, it will come like this. There is something here. We call it what? Hydrogen ATPs. Hydrogen ATPs. Now, this hydrogen ATPs, what's it going to do? It's going to pump this hydrogen that is coming to meet it. It will pump this hydrogen inside this place. Are you following me? So, in the intercalated cell, look at what's happening. This reaction has occurred. It has pumped hydrogen. Now, one thing I want you to know that's common in MCQ is that this hydrogen ATPase pump, it is a high energy pump because it is pumping against concentration gradient. It is pumping against concentration gradient. It is an high energy pump system. Right, that has been done. Now this HCO3 here, HCO3 will leave through a exchanger which we call chloride HCO3 exchanger, or you can say that the chloride channels, anyone to put it. But let's just use chloride channel. Let's use HCO3 chloride exchanger. Let's use that one. That in this place, though this red is not writing very well. Let me see if it's very well. Are you following me? So this thing, this is a jangular, it will move like this. These markers are not giving the colors I need. Let me use this red. If you put power to it, the jangular will go like this. Are you following me? This one will come inside, this one will go outside. So this HCO3 bind to this place. HCO3 minus bind to this place. Chloride binds to this external part. So when we power this pump, chloride will enter, HCO3 will go outside. So that's how HCO3 is leaving. HCO3 will go outside, chloride will enter. That's number 2. What's the number 3 thing that occurs again is that there is also one slight place here in this part, not like this, right? There's one slight place here, and this part allows for potassium to leave. Are you following me? So if they ask you in the late density what's happening, intercalated cell and principal cells are acting. Inside intercalated type cell A, water and CO2 react, H2CO3, hydrogen plus HCO3. Hydrogen is pumped into the lumen. HCO3 is what? These are HCO3 leaves. This thing is called chloride HCO3 exchanger. Chloride HCO3 exchanger. It is exchanging it. It's an antipode. Exchange, chloride enters HCO3 leaves. Then potassium enters into this intercalated cell. Potassium can also leave like this too. Leaky channel. When it enters inside it, it leaks outside like through leaky channels. Is it clear? Aha. So now this hydrogen that now enters is what? Acidic. And open acid is very dangerous. It can damage what? Structures. It can damage structures. Now this hydrogen that enters, so it does not damage this lumen because it's very acidic. What happened? God did a very beautiful mechanism. There are 2 substances in this place. Number 1, we have this one, which is the phosphate, basically, and we also have the what? Ammonia charge. So, sorry, HPO4. Are you following me? So when this hydrogen comes, these ones are buffers, right? When this hydrogen comes, hydrogen will react with this HPO4 minus, which is the phosphate ions. It also reacts with this what? Ammonia ions. So when it reacts, it's going to form H2. When hydrogen reacts with this one to form H2PO4. When hydrogen reacts with ammonia, it gives us what? Ammonium. Is it clear? So basically, that's what's happening. Now, if you look at when you do renal compensation of acidosis and alkalosis, that's when you appreciate this thing much more better. Now, this HCO3 that is entering, now this HCO3 is going outside, right? HCO3 is going outside. It is going to be making the body or the blood alkalotic because HCO3 is a bit to making the body more alkalotic, making it much more basic. That means if you have a situation whereby the body is acidic before, acidosis, the body is in acidosis, this thing will work very important. Don't worry, when you look at renal compensation, you understand what I'm trying to say. This thing will work much more active So HO3 can go outside to neutralize that what acidic nature. So your body can become what? Your blood can become neutral. Is it clear? That's just the importance of this thing. And the higher the acidic nature of the body, the higher this pump works, the faster it works, the more energetic it works. Is it clear? So that's how the intercalated cell works. So potassium is what? Reabsorbed. Hydrogen is what? Secreted. Are you following me? And it is binded to these things. So all these things, they will appear in what? They will appear in urine. So one more thing I can tell you is that people that are having acidosis, like they are in acidotic state, they have maybe any type of acidosis. Let's say respiratory acidosis. You know, if there's acidosis, this pump will work much more faster because we want to throw out HCO3 minus to neutralize the acidotic state of the body. Abi? So when that means in an acidotic state, this pump will be working very well. It will be working with very efficient, very fast. As it is working very fast, that is how it's also going to be releasing hydrogen ions inside this lumen. Do you get it? As this pump is working very fast, that is how it's also going to be what? Releasing hydrogen ions more into this lumen. As it is releasing hydrogen ion excess into this lumen, the more or the rapid the hydrogen binds to this what? These buffers, the more these things are found in urine. Where am I going to? I want to relate it to a concept that when people have metabolic or let's say respiratory acidosis, they always have high amount of ammonium and phosphate in their urine. They always have high amount of this substance because this thing is working very well, efficient. Is it clear? So let's now look at the principal cells. How does principal cell work? Hormone plays a lot of role in this part of the nephron. How does principal cell work? Let me enlarge this principal cell here. Okay, let me use here because I want to still talk about one more thing. Let me use this one here and let me enlarge it. Okay, let me enlarge it. So that's the principal cell. How is the principal cell going to act? Is that first of all, a substance will come, an hormone will come. We call it what? Aldosterone. Aldosterone. This sterone is telling that it's what? Steroid hormone. It's a steroid hormone. Aldosterone means a steroid hormone. Now, steroid hormone can diffuse into cell. Steroid hormone can diffuse into cell. So when aldosterone comes, aldosterone enters into this place. Abi? Aldosterone enters. This one, I can use this explanation I'm trying to do. I can use this one to explain. I just prefer to use this one that is up because it is much more big, so I can be able to draw everything inside. So aldosterone enters. When aldosterone enters into the principal cells, what is going to happen? It is going to code like a DNA, not DNA coding, right? It will code for a protein. It's going to code for protein, meaning to synthesize proteins. When it synthesizes protein, what are those proteins to synthesize? Let me make it more big. Let me clean this intercalated cell here. Let me do it like this. Let me make it in a much more bigger way. When aldosterone enters, it codes for what? Protein. Let's just use what? mRNA. Then what? It codes for what? Protein. Now this protein, they are like channels. They are like what? Channels. So what it's going to do is that it is going to insert channels. That protein, they are channels. To insert channels inside it. Inside the what? Luminal membrane. One channel here. Another, just follow me. Another channel here. Another one here. You see what I'm trying to say? Just follow me, please. Another channel in this place. Let me accelerate. Okay, let's leave it like this. Let's add one more. So it will code for protein. Then the protein form is going to be channels, right? Let's just add one more. Yeah, just make this very well. Now these ones in black. These ones in black. We are going to call them what? ENaC. We call them what? ENaC. Epithelial. E means epithelial. Na sodium. Epithelial sodium channel. Are you following me? They will synthesize protein, which are called what? Epithelial sodium channel. Now, what is the epithelial sodium channel going to do? Epithelial sodium channel will reabsorb sodium. It will what? Reabsorb sodium. It will reabsorb what? Sodium. Those black are ENaC. To reabsorb sodium. Reabsorb sodium. To reabsorb sodium. Why this red? The they will secrete potassium into the what? Into the lumen. They will secrete potassium into the lumen. They will secrete what? Potassium into the lumen. So what am I trying to say is that under the influence of aldosterone, sodium will be what? Reabsorbed. Potassium will be what? Secreted. So that means even all those RAS pathway where we have renin, angiotensin, aldosterone system pathway, this is still basically what we have in the aldosterone. Aldosterone will code for a protein. Those protein are what? Channels. And we call them ENaC, epithelial sodium channels. Look at them here. That epithelial sodium channel, what's it going to do? It's going to what? Allow sodium to be what? Reabsorbed. Right? As it is taking sodium inside, it is taking what? Potassium outside. Sodium inside, potassium outside. Sodium inside, potassium outside. So all this potassium, they will what? They will enter into what? Urine. They will be inside what? Urine. Are you following me? Why the sodium can have sodium potassium ATPase pump here? Pumping sodium out and it's pumping potassium in too. So this potassium that is coming in, it will also move through this potassium channel. Are you getting what I'm saying? We have a sodium potassium ATPase pump. All this sodium that is coming, they leave. Are we now? Why the potassium enters? The potassium that enters, it will also lead to your potassium channels and enter out in the urine. Are you following me? So the urine will have what? High amount of potassium, while the blood will have what? Less amount of potassium. The urine will have less amount of sodium, while the blood will have high amount of sodium. Let me come again. Under the influence of aldosterone, the blood will have what? More sodium, and the urine will have what? Less sodium. Under the influence of aldosterone, the urine will have high potassium, while the blood will have what? Low potassium. And the amount of sodium reabsorbed there is about 8%. It's about what? 8%, right? Aha. Now let's now look at one more thing. Let's look at the effect of ADH. Effect of ADH. This is where we are going to basically put it to a major end. Effect of ADH. How does the ADH act on this thing? ADH is work. ADH is called diuretic hormone. Uretic means urine, right? Anti means against urine. So ADH is basically an hormone that prevents you from urinating. Are you following me? So ADH acts for what? Water reabsorption. ADH acts for water reabsorption. I also forgot to told you that water is reabsorbed. All those, you see all those parts I was explaining in the PCT and the loop of Henle, thin descending loop of Henle. Water is reabsorbed using aquaporin 1. Yes, using aquaporin 1. Aquaporin 1 protein. So let's look at this principal cell. How does ADH act on principal cell? How does ADH act? Let's make it to be bigger too. How does ADH act on principal cell? How does ADH act on principal cell? I forgot to add that this aldosterone, what is it carrying inside? Sodium. It is carrying both sodium and water. It's carrying both sodium and water. Now, anywhere sodium go, water follows. It's carrying both sodium and water. Now, let's look at how does ADH act on the what? On the principal cells. So first of all, we are going to have a receptor, a serpentine receptor, or you call it a 7-pass receptor. Let me draw it this way. Okay, 1, 2, 3, 4, 5, 6, 7. Are you following me? A serpentine receptor following the GS system. It is a GS protein. Now, ADH comes. This is ADH. ADH comes. ADH binds to this what? It binds to this serpentine receptor. I will keep it very basic. Inside these principal cells, there are something we call filaments. Look at. Are you following me? Now this thing is having some channels like this. Just follow me, please. It's having some channels like this inside. Are you following me? So on this part, on this basolateral membrane, we also have some channels here. Let's just draw something very few. We have some channels in this place. Are you following me? So when ADH binds to this receptor, the receptor is called V2R receptor. V2R. When ADH binds to this V2R receptor, information will go like this and enter into the cell. When the information enters to the cell, it will send the signal to this what? To this filament containing these channels. Now, when this information gets inside, this thing, all these filaments, they leave. They will leave. They are going to leave. They are going to leave. Are you following me? They will leave. Now, when they leave, these channels have become what? They have become free. Now, when these channels become free, they will come and insert themselves on this place. They will, that means all this thing that was here before. When ADH binds to them, they become free. Then they come and insert themselves here. That means before, without ADH, these channels were not here. Without ADH, these channels are not in this place. And so they are now here now, under the influence of ADH, right? So we have them here. So when they insert themselves here, what are they going to be doing? They will allow water reabsorption. They will drag water. They have inserted themselves in this place. They will pull what? They will pull water. Only water. No, only water. This one of aldosterone is pulling what? Sodium and water. But ADH is pulling what? Only majorly water. So water will be moved. So that's how water is reabsorbed too. Water is absorbed at the front part and this place too. Now these channels, they are called aquaporin 2. They are called what? Aquaporin 2. Aquaporin 2 channels. Now aquaporin 2 channels will only exist on this luminal membrane when ADH comes. If ADH does not come, this aquaporin 2, they will never be inserted on this luminal membrane. When they are not inserted on the luminal membrane, they cannot what? Reabsorb water. So now after this aquaporin 2 has reabsorbed water, the water has entered here. This water will now leave. They will leave through what? Through this place. The water will leave through this place. Now these channels, this one are called aquaporin 1. The one are called what? Aquaporin 1. The one here are called what? Aquaporin 2. Now this aquaporin 1, they are always present even without the influence of ADH. But aquaporin 2 will only be present in the luminal membrane under the influence of what? ADH. Is that clear? So basically, that's how the whole reabsorption process is occurring. I would have loved to take diuretics, but the video is getting long. I'm going to end it at this point. So in my next video, we'll be talking about countercurrent mechanism, right? We'll talk about the concept of urine dilution and urine concentration, and I'll talk about diuretics. How does, okay, should I really brief it? Okay, PCT, on the PCT, the diuretics that work on the PCT is called acetazolamide. Though I will explain that mechanism in my next class, but let me just list it. The diuretics that works at this PCT, they are called acetazolamide. The diuretics that works at the loop of Henle, they are called what? They are called loop diuretics. Loop diuretics. Example is what? Furosemide. A diuretic that works on the LEDCT is called thiazide. Thiazide. Yeah. A diuretic that works on this last part is called alcohol. Yeah, alcohol is also a diuretic. Yeah, basically. Yep. So I think I will stop at this point. So in my next class, I'll talk about the mechanism, urine concentration dilution. Then now I don't talk about clinical correlates. Yes, because in this renal physiology series video, the last video I'm going to do, I will talk extensively on clinical correlates alone. I'll talk about renal abnormalities alone. Is that clear? Thank you for watching. See you in the next video.